Alright, here we are, Fundamental Theorem of Calculus, also called FTC for short. Consider the integral from a to b of some function, and just recall that the integral is the area under the curve. And so if we just kind of put a visual to this quickly, let's see if I can get a different color. Our goal today is to try to find a way to find the exact area under the curve. And this is the proof that's going to get us there. So we're going to let g of x equal this integral from a to b of f of x dx. And then we know via some definitions that g prime of x must equal f of x by definition. Remember, you can think about this as if you look at this and you take the derivative of both of these things. The derivative of an integral, the derivative of an integral is going to take you back to the original function. And so we can say that g prime is equal to the argument here. Let me switch back to my other color. So we now can say, since g is differentiable, remember differentiable means it has a derivative, we can apply the theorem that we talked about yesterday, the mean value theorem. And that sometimes is called the MVT. Okay, I'm going to move forward to next page, and what we're talking about is the MVT. So let me just kind of set up a quick picture of what we're working with. And so if we're trying to find the integral of some interval a to b, we are going to divide the interval a to b into n subintervals, each with width. That's kind of fun to say. Delta x. And so, if I come over here and think about this, a lot of times we've talked about how we want to cram in an infinite number of rectangles in here, but it's going to be hard for me to draw an infinite number of rectangles, and so I'm just going to draw a couple, and then we'll kind of see where we go from there. And so if I draw a rectangle in here, I'm going to call this line x1, and I'm going to call this line x2, and then cram in a bunch here, and I'm going to call this line x n minus 1. And the reason it's n minus 1 is sometimes bothersome, because over here we're dealing with n subintervals. But if we can kind of just think about this very quickly, if I ask you to break this interval here into 3 rectangles, 3 rectangles would come from two vertical lines. And so, you know, if n was 3, as in 3 rectangles, we only have to construct, you know, 2 vertical lines, and that's why this is n minus 1. I'm also on this diagram over here going to put in some c values. You know, I'm going to call this my first c value. I'm going to call this my second c value. And somewhere in here, you know, in my third rectangle, I'd have my third c value. My fourth rectangle, I have my next c value. And when I finally get to my last rectangle, my nth rectangle, I'd have my nth c value. And the reason these are going to be relevant is we're going to let C1, C2, C3, C4, all the way up to Cn be the C's in the mean value theorem. So recall just quickly that the mean value says that if you have a function that's differentiable and continuous at its endpoints, then there's some c value within that interval that the slope at c is the same as the slope between the endpoints. And so let me kind of draw another picture here, a lot of pictures today. If we kind of zoom in real quick here, you know, on part of my function, you know, I have my a value here, and then you know, my first rectangle, talking about this position over here, is x1. And the idea is, let me switch colors so we can see it really well, or at least try, is that if we set up the slope between these points, that there is some c value in there, you know, that shares that slope, that has that slope. Okay, so I think we have all the background to kind of to start making some conclusions. So I'm going to move to another page, and then again, I guess this is a video, so you can rewind or whatever if you want to see these pictures. Let me move. Whoops. Let me move forward, and I can say since G is differentiable, that was the criteria for the mean value theorem, and we know it's differentiable because by the definition of antiderivative, G prime is f. That was on page 1, you know, a couple minutes ago. But since G is differentiable, the mean value theorem can be applied. And here we go. I can say that G prime of C1 is equal to G of x1 minus G of a over x1 minus a. And again, if you forgot the picture already, kind of referring to this picture right here, the slope between x1 and a is, you know, we're talking about the slope between x1 and a over the, you know, horizontal change, x1 minus a. And the mean value theorem says we can, you know, take the slope at c and make it equal to that. So that's what I'm using to get this piece right here. And if we slide over to the next rectangle, and our next c c value would be the slope between x2 and x1 over x2 minus x1. And if I did, g prime of c3, I'd have x of 3 minus x of 1. But I don't want to write an infinite number of these slope formulas. So I'll jump straight to the last rectangle, which says that g prime of cn would be g of my end value, g of b, minus g of xn minus 1 over b minus xn minus 1. Again, just to refresh, and you can fast forward if you're sick of it, but I'm talking about this last rectangle where this is b, this is x to the n minus 1. There's some c value in here that we're calling cn, and we're finding this slope, and then we're saying that there's some other slope in here. That's what this means. Okay. All right. We're going to go to one last page here, and we should be able to finish it up. So, moving on. Fresh sheet. One last recall. I'd like you to recall that the Riemann sum, R sub n, is defined as the sum from 1 to n of f of c times delta x. And just remember that f of your c values, you can kind of think of these as your heights. And remember, your delta x are your widths. And so, just to expand this out a little bit, we can think of Rn as f of c1 times delta x plus f of c2 times delta x plus f of c3, sick of this yet, delta x. And I don't want to write all of them, so I'm going to jump straight to my last one, which is my nth height times delta x. And now the magic is going to start to happen. So, if you scroll back a couple pages, I can do that quick. F is G prime. F is G prime. F is G prime. Say it with me. F is G prime. All these F's on this page are G primes. All these F's are G primes. And so, I can rewrite this as G prime of C1 delta x plus G prime of C2 delta x, G prime of C3 delta x. We're using substitution here, but the notation looks a little bit crazy. G prime of Cn delta x. So that's pretty exciting. But these G primes of C's, are represented on this page. So I have G prime of C1, G prime of C2, all the way down to G prime of Cn. And this is where we used kind of the slope formula. So because I have all these beautiful colors, let me kind of rewrite this. We discovered that G prime of C1 was, if I can remember it, G of x1 minus G of a over x1 minus a times delta x, plus the next one was G of x2 minus G of x1 over x2 minus x1 delta x. And now mathematicians are lazy, so I'm not going to write this third one. You can write it for fun if you like. And then I've got g of, what are we looking at? B minus g of x in minus 1. I think that's right. B minus x in minus 1. Delta x. All right. So we're almost there. It looks worse than it was, but it's about to clean up nice. If I go back to this picture, I believe, this page, can we find the mystery? I'll help you find it. When we initially divided this, we divided the interval into n subintervals, each with width delta x, each with width delta x, which means all of these rectangles in here, each of them have a width of delta x. That means that this width is delta x, the next width is delta x, that means this width, if drawn to scale, was delta x. But if you look up here, that means that x1 minus a is delta x, and x2 minus x1 is delta x. Are you gasping in excitement here? All of these denominators are delta x's. So, big reveal. All of these, uh-oh, my eraser's a little bit out of control. All of these, oh no, I forgot to switch back to my pen. All of these are delta x's. All of my widths are delta x's. Let's fill this back in. We had g of b minus g of x in minus 1. But now that width is a delta x. And behold, we have some simplification that's in order. And now I can write Rn as g of x1 minus g of a plus g of x2 minus g of x1. Just for kicks, I could write g of x3 minus g of x2. And in the very end, we've got g of b minus g of x in minus 1. And I hope that you see that we've got some stuff that cancels out. We've got a g of x1 and a minus g of x1, so that's gone. We've got a g of x2 minus a g of x2, that's gone. G of x3, somewhere in these dot dot dots, we're going to get rid of an x3. G of a is sticking around. G of b is sticking around. G of x in minus 1, again, is going to be somewhere to the left of g of b. And what we have left is g of b minus g of a. And that is the fundamental theorem of calculus. If you just want the proof, then there you go. If you want to stick around, let me kind of explain what we discovered, because sometimes we get lost in the notation. Okay, so if you're still here, let's explain exactly what we found so we understand the power of the fundamental theorem of calculus. Remember what we started with was defining this integral from a to b of f of x as its own function g of x. And by definition, we said that the antiderivative g prime is equal to f of x, and we went through a whole bunch of steps. But at the very end we found out that this Riemann sum, and the Riemann sum, is the definite integral. We found that it can be defined as g of b minus g of a. And so let me kind of just explain, hopefully explain this in words, the power of this. G is the antiderivative of f. Whoop, I left off my f. And what this says up here is that all you have to do to find the exact area under the curve is find the antiderivative and then plug in the endpoints and take the difference. So you guys at this point know how to take antiderivatives, and so you're going to be using all of those antiderivatives and evaluating them at the endpoints of the definite integral, and it'll give us an exact answer for what we want. So let's just kind of do a quick example. Let's mix it up a little bit. Let's say we want the integral from 0 to 4 of x cubed dx. Always, always, always think about what you're trying to find visually. X cubed, you got your classic cubic function heading up towards infinity, and you're asked to find the integral from 0 to 4. You're supposed to be finding the area under the curve from 0 to 4. My area doesn't look very big because I kind of squished the graph down here, but 4 cubed would be 64. And so just to add a little more context, we're trying to find the area of that purple space. So the antiderivative of x cubed is 1/4 x to the 4th plus c. Don't forget your plus c. And so if we're kind of using this notation up here, the claim is that this is our g of x. This right here is our antiderivative. And so what the FTC says, I'll put by the fundamental theorem of calculus, we can take this antiderivative with this 1/4 x to the 4th plus c, 1/4 x to the 4th plus c, and we can substitute in our endpoints. Right. This is me looking at g of 4 minus g of 0, right? Because this was our g of b minus our g of a. And when I evaluate these, I've got 1/4 times 4 to the 4th. Do we have our 4 to the 4th memorized? Was that 256 or something? We could actually just cheat and say, well, I'm going to cross out one of these 4s. So 4 to the 3rd is 64, and minus, I like this, 0 to the 4th times 1/4 is 0. And people always worry about these plus c's. We've had some arguments, or not arguments, but discussion about them. But when you plug in this value for, when you plug in this 4 and you plug in this 0, these c's kind of represent the same function, this antiderivative function that we're calling g of x. And so the c's actually cancel. The c minus this c, it represents some actual value. They cancel, and with definite integrals, they're always going to cancel. And so we really just care about the numeric value. And what I have here is 64 minus 0. So the answer is 64. Pretty baffling, pretty exciting just to recognize that this area of this goofy shape that has a curve, the exact area of that is 64. And that's the fundamental theorem. Thanks for watching. Thanks for checking it out. If you're judging this, it's my first go, and I did it in one take. So give me feedback if you want, but thanks. Have a good night.